Jingle bell, jingle bell rock. Embedded Adventure Day 12. Hey. I hope that wasn't too cringe for you to shut the video off. Yeah. So again, Embedded Monk here. Embedded Adventure Day 12. Where I am as a complete beginner trying to learn embedded stuff, trying to program that little tiny thing called esp32. We have already done a lot of things. Already done the HTTP remote LED control, already done some HTTP client requests, the traffic light, that was also pretty cool. And in the last series, on Embedded Adventure Day 11, I have written the plan, the further plan to learn the embedded systems. So I divided it into two sections, theory and projects, but today I guess we're gonna go with theory, and the reason is I just want to explore this topic, the FreeRTOS. I'm actually not very pro at multi-thread programming or something like that on a usual personal computers. And here we're gonna try to do some multi-thread or parallel stuff on the microcontroller. So I guess that would be cool. And without any let's go. So actually I'm gonna use ChatGPT a lot today because this topic is actually interesting for me. So I'm gonna prompt a lot. So I hope that won't bother you guys, because I still think that ChatGPT is a wonderful tool for learning. Not for copy-pasting, but if you just ask and explore topic, that's cool. Also, I probably will go to the random nerd tutorial, because I heard that I saw there the tutorial about the FreeRTOS. Probably I should check it out first. And when I will, and also I guess we'll need some docs here. Not docs like animals, but docs like papers, ESP, expressive, that type of thing. Materials, yep. Yes, official ESP documentation. Here we go. Okay, so, well, I can basically Google it, I guess, like FreeRTOS esp32. Yeah, so actually I guess the main reason, of the of all of these videos with the Embedded Adventure, just to show that I am just as a complete monkey. That's why I called actually my channel Embedded Monkey, that every monkey can learn embedded systems if he is consistent enough. So first of all, I want to explore the topic of FreeRTOS. Can you make a plan for it? FreeRTOS programming for ESP32 and RTOS in general. Yeah. By the way, I probably should also provide some materials for you guys, because I also make some notes on my Google Drive, but I haven't done them in a while, so probably that would be a good reason to do that. Okay, so the structured plan, C programming, basic embedded concepts, we already know that. Well, I know some basics of interrupts, some basics of timers, but probably that's a good point to actually repeat those topics. Probably I can find some tutorials here about them. Okay. DIY cloud, what? Yep, interrupts timers, I guess that's what we need here. Okay, let's check. Hell no. Okay. Oh, I guess this is a tutorial for Arduino IDE. That's not like for the, well, I hope they actually will introduce something here. Some main topic, main idea. Useful for making things happen actually in microcontroller programs and can help solve timing problems. You don't need to constantly check the current value of a pin with interrupts when a change is detected. An event is triggered. Function is called. Well, basically, yeah, that is the main like idea of interrupt. So when some event happens, it just basically places the address of this event handler on the stack, and which is basically a function call. And then when it's done, it just gets back to the program. So that's basically an interrupt. Yeah, so that is the main idea. Okay, and the timers, I guess they just want to say that the number of ticks is somehow equal to number of seconds in real time. Yep. So the CPU cycle, so the CPU ticks is actually well, let's read. Yeah, let's read first. I'm not really sure to give you some information here. In the example, we'll also introduce timers. We want the LED to stay on for a predetermined number of seconds after motion is detected, instead of using a delay function that blocks your code and doesn't allow you to do anything else. For a determined number of seconds, we should use a timer. Okay, is something loading here or no? Okay, that's strange actually. By the way, yeah, okay. You should be familiar with the delay function. Okay. When you call delay, your program stops on that line for 1 second. It's blocking function. Blocking functions prevent a program from doing anything else until that particular task is completed. If you need multiple tasks to occur at the same time, you cannot use delay. Well, fair enough. The millis function. Third over using delay. Sorry guys. By the way, it's 12:30. Like, damn, it's so damn late. Using a function called millis is preferred over using delay. The millis function returns the number of milliseconds that have passed since the program first started. So Matthew can easily check how much time has passed since a certain event without blocking your code. So current millis. Okay. And then we just digital write the lat state here in the loop while, okay, I got the idea. It's like the time function in C, I guess, the basic C function here. But in general, I would like to know a little bit more about timers than just a simply millis function. So yeah, okay. ESP32 basics, we already know a lot of basics, so we won't go here. And finally, RTOS fundamentals. Understand why RTOS exists and how it works. So bare metal versus RTOS, deterministic behavior. Okay. Scheduler preemptive versus cooperative scheduling. Okay. Core API. Create, delete, delay. Okay. So basically a task management. Okay. Inter-task communications. Okay, that's quite familiar. Things like use semaphores, mutexes, FreeRTOS architecture, and send it special. Okay. Now we probably won't go that deep. I probably will stop on the, I know, on this level. Maybe, I don't know, here safely combine interrupts with RTOS. Well, maybe learn a little bit about interrupts more. But probably we're not gonna that deep here. Probably it's better to actually do that stuff on some real project. So I know some of basics about timers and interrupts. Can you help me to recall some things, like to recall these concepts? Yep. Well, yeah, basically that's it. That's all you have to know about hardware timers. Actually, just a counter that counts up every clock. Yep. And by the way, that's interesting. I actually found that thing in the, I guess in the datasheet or in the reference manual. I don't really know. Let's go here. Okay. Probably here I saw that. Okay. Damn, too long. By the way, what? They made a ChatGPT inside PDF document. Here. Whoa. Or is it like the it's esp CPD docs AI, the custom large LLM model trained on official documentation from Espressive. Yo, that's cool. That's cool. Well, I probably won't really will need it much. I just want to actually find the clocks here, like, because I saw like the APB clock at least once here when I was learning how GPIO works. Yep. Probably it was in the GPIO section. No. That's I2C thing. The main clock. What is it about? Remote control. No, I definitely haven't seen it here. But okay, yep. Let's just continue exploring the ChatGPT stuff. Okay. So we got 3 different clocks that can drive the hardware timer, yep. Some prescaler that divides the clock, the counter, and the comparator. Okay, so prescaler, counter, then event, then interrupt flag. Okay. Thinks at 1 megahertz compare value to everyone. Oh yeah. If we know that the clock has the frequency of 80 megahertz, it's just basically Each period is 1 divided by 80. I don't know how much is that of a second, but it's pretty very small value, extremely small value. So it's like 1 divided by 80. So yeah, it's like that small. It's like 1/100th of a second. Yep, basically extremely small value, and this is a period. So if it ticks at 1 megahertz, 1 megahertz is basically a 1 second. Yep. Or what? No, megahertz. Yo. That's like 1 divided by 80 and divided by 10 to the power of 6. So that's even smaller. Yep. So not even that value. It might be divided by like 1 million. That is actually the period of that clock. Okay. So, okay. We've done some math. Okay, common timer modes. One shot runs once, then stops. Used for timeouts. Okay. Periodic autoload resets automatically. Used for OS tick, sensor sampling, LED blinking, PWM. Yeah, I probably heard about it in the PWM. Probably it was on when I learned the Let's See controller. That's where I saw these clocks. Here we go. Yeah, that's like the inner structure of a channel, and here we have some basically a timer for every channel. Yep. Here we go. By the way, that would be interesting to actually learn that stuff, because I stopped when I understand it how it works on this level. So it was when I done like the first LED blink ever, like my simple my actual Let's See PWM. Yeah, that stuff. So when I finally learned what each of these fields mean, then I finally actually completely understood that stuff. But I haven't gone that far to know how the timers work, so probably I should actually do that theory. I hope I will find some time for it. Okay, so let's continue exploring that stuff. So, got the periodic timer, the PWM. Okay, very important. So, not scalable, interrupt driven. Not scalable, interrupt driven CPU does other work. Yeah, so probably the main thing is that we can programmatically make a delay for example, number of ticks. I don't know, like 1,000 ticks, for example, yeah? And then live that loop. Or we can actually leverage that thing on the CPU timer, and it will do some work. It will do some work for us. Yep. While we can execute actually main tasks, and then when the timer fires, we get the interrupt. Okay. What an interrupt really is. An interrupt is a hardware signal that pauses current code, saves CPU context, of course, it's just on the stack, jumps to an ISR, interrupt service routine. No, that's how it's called, okay. I thought it's just called interrupt handler, but okay. Okay, so we jump on it, return to where it left off. Okay. Asynchronous, high property. Okay, I don't really get that thing. Like, what is the flag? What is the timestamp here? Okay, so it should be fast. What does it mean it should be fast? Like, fast in terms of what? In terms of it doesn't do much work, or what? I currently don't really understand. Interrupt service routine. What belongs in an ISR? So we set a flag, we send a signal, we capture timestamp. Carry combination blocking calls, printing. So probably that's just an example of what can interrupt do internally. It can set some flag, it can send some signal, it can capture some timestamp, but it's really not about heavy computation, not about the blocking calls, and not about printing, definitely. Yeah, I agree, because interrupt are meant to be asynchronous. Okay. ISRs must be sure to interrupt latency time between event and ISR execution affected by CPU speed, disabled interrupts, higher priority. Okay. Yeah, by the way, ISRs also have some priorities. Okay, yeah. SARS cause missed interrupts, jitter, RTOS scheduling problems. Okay. Drops in priority. Can interrupt others. Wins. Yeah, by the way, interrupts have priorities. So basically, the higher the priority, the more likely this interrupt to interrupt other interrupt. So this is like the main thread. Then we interrupt it. Then we have some other thread on the stack, and then we interrupt it again. And if this priority was higher, it is not rejected and get interrupted. And if it was lower, we just continue. Probably like it should work like that. Well, it's basically better to draw. I'm just trying to remember because I had some knowledge about how it works. So basically, this is like the main thread, I guess. Main. Oh, that's terrible. That's terrible. That's terrible thing. Okay. Basically, that's like the main. Oh my god, that's even worse. Okay, main thread. Yo. Okay, main thread. Here the timer fires. Yep. Timer fires. Just for me to better understand that thing. Like, okay. Timer fires. Fuck. Okay. Timer fires. Yep. Okay, perfect. Then we get some interrupt here. So we go with the interrupt. I don't know, let's take the green one here. Okay, or I don't know, orange one. Yep, orange one. Get here. Here is the interrupt thing. Yep, so this is like the interrupt. As far as I understand, interrupt. I don't know how it works. Interrupt, yep. And then we can have another interrupt here. Another completely different interrupt here. And if its priority is like blue, it's, well, like blue lower than orange, you know. It's like we reject it, and if it was higher, then we accept it, and make another interrupt here. Or just reject and continue. Yep. Okay. Fair enough. But I guess usually we'll have the picture more like this. So we have done some work. So okay, like just basically some work. Yep. And actually some simple work. So setting some flags, signals, or something like that. Yep. And then we're just getting to the main thread again. Yep. Continue our work. So basically exiting interrupt, exiting ISR. Yep. Okay. Cool preview, by the way. I probably will put this on as the preview of this video. Okay. Right. So this is like how timer plus interrupt based event works. So timer expires, then interrupt fires, then we set some flag or send some signal, then back to main logic. Probably that's like one of the most simplest ways to actually make the parallel, to make asynchronous stuff. Yeah. Like even without RTOS it will work. Volatile, okay, critical but often forgotten. Those shared between ISR in normal code must be volatile. Okay, yeah, probably. From bare metal. Timer ISR sets flags, main loop checks flags. Timer ISR. Two events ISR signals. Tasks do work. Okay. Timer ISR wakes, sends a queue item, gives a semaphore. What runs next? So RTOS is basically a timer interrupt events, but more advanced. Yep, more advanced. Okay. So I guess that's a cool theory, and I want to do actually some experiments. Okay. Can you give me some experiments that I can do to understand it better? What to observe and what to learn. Okay. Polling versus timer interrupt baseline. Okay. Feel why interrupts are better than polling. LED on GPIO. Or timer at 100 seconds. Measure timer accuracy. Well, that's not very interesting experiment for me. Learn proper ISR design. Does full processing. Flag mainly process the data. I guess the cool thing that we can actually do right now is to make an LED blink by the interrupt. Yep. So let's just basically create a new project. Yep. Okay. Embedded adventure, day 12. Create. Okay, project. Let's call it, I don't know, ISR experiments. Yep. Why not? ISR experiments. So the actual thing that this program will do is to just basically blink an LED. Yep, so I basically will copy paste that thing here, but it should not, okay. Okay, let's sorry guys. Oh my god. Woo. Okay, throat is fine. Let's continue. So, the actual thing that I want to do is to blink an LED for every delay seconds. The shining period and delay can be the following, and we just want to not use the RTOS. We are forbidden to do that. RTOS VTask delay is forbidden. Yep. And the regular delay function, so something like that, well, it's also forbidden. Yep. Let's assume that we only have our interrupt thing. How can we actually make an interrupt handling using the esp-idf framework, of course? esp-idf interrupt allocation. Yep. So now we're moving on from like plain theory to how can we implement it on esp32 chip. Yep. Both programmatically and by the way, that would be cool to know how it works here, like on the low level. Memory. I just wonder, does it have some chapter that is about the interrupts? Well, what the fuck is that? Oh, again, waiting for a long time. Guess, okay, so I'm just gonna, oh man, no me, oh. Just don't want to waste so much time on it. Okay, let's just read here a little bit about how to do it programmatically, and then we'll look on how it actually works on the hard bare metal level. So, okay, has 2 cores with 32 interrupts each. Each interrupt has a fixed priority most connected to the interrupt matrix. Okay, because there are more interrupt sources than interrupts. Sometimes it makes sense to share an interrupt in multiple drivers. The ESP interrupt allocate abstraction exists to hide all these implementation details. Okay. Let's look. Here we go, interrupt matrix. It described here. Just want to read how it works. So The interrupt matrix embedded in the esp32 independently allocates peripheral interrupt sources to the two CPUs. Peripheral interrupts. Okay. This creation is made to be highly flexible in order to meet any different needs. So let's look at the schema. Peripheral interrupt. Okay. "71 peripheral interrupt sources in total." Okay, all peripheral interrupt sources are listed in this table, so probably can take a look. Oh, whoa, 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 whoa. Yep. Okay. So, as we can see, there are lots of interrupts here, but we have only 2 interrupt peripheral inputs. Or is that about outputs? No, just 2 CPU peripheral interrupts, like 2 kinds. Okay, some Pro and some AP, app CPU and Pro CPU. Okay, peripheral interrupt sources as input generates 26 peripheral interrupt sources per CPU as output. CPU interrupt matrix. Okay. Well, I would like to know what's inside that box, but I currently don't really get why do we need some matrix here. All peripheral interrupt sources are listed in the table. 7 of those can be allocated to either CPU. The 4 remaining peripheral interrupts are CPU specific to per CPU. Oh, so 67 of them can be actually used in any of the cores, because ESP32 is double cored, and the 4 remaining peripheral interrupt sources are CPU specific. So, okay, 2 per CPU. Okay. By the way, probably we need the GPIO interrupt to actually do some things, probably somehow related to GPIO if it's called so. Yeah. Interrupt. Use have 32 interrupts each, of which 26 are peripheral interrupts. All interrupts in this CPU are listed in this table. So this is actually an interrupt kinds that we can use on each of cores. Yep. Peripheral level trigger timer. Okay guys, probably need to go to drink some water. I'll come back in a few minutes. Okay. Don't say goodbye. Okay guys, I'm back. Let's just continue reading that thing. Well, to make it more epic, let's actually code it, and then maybe today, maybe I'll do it by myself, and I will do some notes on that part of the reference manual, because it's actually an essential topic as far as I know for an embedded thing. But firstly, oh my gosh. Whew. Let's code it. Oh my god, I'm just literally dying right now. Sorry guys. So, this function allocates an interrupt. What does it mean to allocate an interrupt? I'm wondering, like, what does it really mean? Where can I find it? Okay, the same thing. All right. So I guess there is not actually much API here. What about the header? Can we just... Oh, just plain header. Thanks a lot. But we can actually find this function here, just to take a look. Damn, seems like a very large header here. Okay, let's just read that stuff. Sorry guys, I'm just a little bit ill, but I hope you won't mind. Okay. That's a fixed priority. Because there are more interrupt sources than interrupts, sometimes it makes sense to share an interrupt in multiple drivers. The esp interrupt alloc abstraction exists to hide all of these implementation details. Alright. Okay, so a driver can allocate an interrupt for a certain peripheral by calling the esp interrupt allocate. Yep. But we can actually also call allocate bind. Get interrupt status bind. You can use the flags passed to this function to specify the type, priority, and trigger method of the interrupt to allocate. Okay, the interrupt allocation code will then find an applicable interrupt. Use the interrupt matrix to hook it up to the peripheral and install the given interrupt handler and ISR to it. Wait a second, so you can use the flags passed to this function to specify the type, priority, and trigger. Application code will then find an applicable interrupt. Use the interrupt matrix to hook it up to the peripheral. Install the given. So basically, this matrix is managed by some smart inner algorithm that, so you pass the type, the priority, and what peripheral you want to bind, and it actually somehow make a search for that matrix and find an a good option for setting this interrupt on this peripheral with such type. Probably, yeah. You know, let's ask. What does it mean to allocate interrupt? What is like interrupt matrix? And how the interrupt is actually being set in esp32. Yeah, probably I should actually send it like the technical manual reference, but we're gonna go with it. Okay, go below the API level layer and really clarify how esp32 works. Okay, I mean, assigning a hardware interrupt source to a CPU interrupt line, attaching an ISR to it. Which event can cause an interrupt, timer, GPIO, UART, etc. Which CPIO interrupt line it uses. Which function ISR runs when it fires. This is fixed, it's all configurable, okay. So interrupt source versus CPU interrupt. Comes from a peripheral. Root 0, timer 0, GPIO pin 4. Okay, CPU interrupt line. An entry point into the CPU has priority level, type, so on, so on. Who knows this? Connecting a source to the CPU line to the ISR. Okay, so we bind the source, then in CPU line we bind the priority and the group, and then we bind the actual handler. Okay. The esp32 has a programmable crossbar between peripherals and CPU interrupts, so I guess I got it. One moment. So programmable crossbar between peripherals and CPU interrupts, peripheral interrupt sources, interrupt matrix, CPU interrupt lines, ISR. I guess I somehow starting to get this thing. Yep. Let's esp32 route any peripheral interrupt to almost any CPU interrupt. Okay. And actually support dual core routing. Using interrupt matrix. Each peripheral has a fixed interrupt line. Okay. Through what happens behind the scenes when you register an interrupt. Peripheral raises an interrupt. Timer reaches compare value. Sets its interrupt flag. So it's okay. One moment. So register interrupt mask. Okay, so this is the interrupt sources. These are actually the interrupts that we can bind to. Here we go. So this matrix actually has a very huge size. We have these much of interrupt sources. So 68 interrupt sources altogether. And we have 32 available CPU interrupts. So this matrix actually allows us to configure 68 on 32, 2,176 different interrupts. As far as I understand. Yeah. And these sources are actually all different events. So we have some SPI, I2S, some lat C interrupt, even some lat C interrupt. But I thought there will be like a GPIO one. I can't see the GPIO interrupt here, or maybe it's reserved for some reason. Or maybe I just skipped it. Yo, I just skipped it. Here they are. GPIO interrupt pro, GPIO interrupt up. So there are like 4 of them here. And by the way, there are actually 69 of them. 69 plus 1 plus 1, 71. 71 interrupt sources. Okay. And they can be actually used. Like, no, 67 of them can be used. Can be allocated to either of CPU. Yep. So these ones use these registers for, I don't know, for a status register. Yep. Either of them. Here's a configuration register for them. Okay. Here is again the configuration register. Alright. Here we got some other one. They use some. Oh, I guess I got it. They use like the different halves of the register probably. So this one uses the first 32 bits. This one uses the second 32 bits, and also there's a register that uses only those 5 bits, and that's all basically. Okay. Well, I actually want to somehow configure it bare metal. I don't know why. I just want to know what all these registers mean. Like, okay, one moment. Here is a photo. Here is a screenshot from official esp32 technical reference manual. Can you explain all of signals here, and what is the difference between pro I don't know, like pro CPU and app CPU. Yep. Pro CPU and app CPU. What's like the main difference? There is exactly the right one to study. I'll work through signal by signal. Okay. So pro CPU versus app CPU. Protocol core, application core. It's two identical extends the cores, but they play different system roles. Okay. So Pro CPU Core 0 is a bootloader, Wi-Fi, Bluetooth, some system interrupts, App Core 1, user application tasks, most free RTOS tasks. I thought they are more like equivalent. Have like thought that they have like different responsibilities. But okay. What the interrupt matrix does. The interrupt matrix is a programmable router. Yeah. Okay. So yeah, I understood that we actually bind the peripheral interrupt source, which are actually 71 of, or 67 available for different purposes, and we bind it to some CPU interrupts, which are 32, and we can actually configure them via probably via the some interrupt mask or something like that. Well, let's check. Interrupt line or app CPU interrupt line. Each core has its own view of interrupts. Let's go through the diagram signals. I'll follow the diagram left, right, bottom. Okay. So peripheral interrupt source, left side. This is the raw interrupt signal generated by peripherals. Okay. Timer, GPIO. Yeah. We have already seen all of them in this big table. So these do not go directly to the CPU. These first go to interrupt matrix. Okay. Interrupt matrix center block. This block selects which CPU gets the interrupt, selects which interrupt level it uses, and applies masking and routing rules. Okay. Configure switch board. Okay. Yeah. So probably that's like the main task of interrupt matrix to route the peripheral interrupt to the right CPU with the right level and with the right priority. Yeah. Configuration signals. Okay, so Pro CPU peripheral interrupt configuration register controls which peripheral source is mapped to which Pro CPU interrupt number at which priority level. So this register is basically the main register here. So in this configuration register, we basically, well, we can actually look it up. I guess Pro CPU. Let's just, I don't want to open it again. I don't actually want to open it again, please. No. Just wait again for that endless loading. Okay, I will just look it up here quickly. Pro CPU. Dboard Pro interrupt status. No, that's a status register here. We need the configuration one. Configuration thing. Pro CPU interrupt. No. Configuration one. Yeah, we need a configuration. Guess that's like not the right register here, and we basically don't have any like, you know, info about it. Pro CPU. No, not here, definitely. Maybe this? No, not this one. Interrupt status. No. So, by the way, let's use that thing in the corner. They haven't probably added just by accident, like, find me format of pro CPU configuration register. By the way, working with documentation is like #1 skill, I guess, when learning. Is not a unique name in the manuals, but from the context of your documents, it most likely refer to pro CPU interrupt configuration registers. Yep. Map register. We'll share the same format. Register. Reg summary. Go here. What the? Okay. Well, I can find it by myself, actually. I don't really need that strange link, I guess. I currently don't know, so I can't really rate that thing here. Okay, just map register. Here we go. No info. No info. Oh my god, no info about it. So we can only, well, probably they use all the shared format. Yep. Probably, yeah. Okay, so the source you provided do not include a bit. Well, okay, I somehow understood it. Okay, so we configure that register. We put there their peripheral source, the number probably. Then we put the interrupt number, the priority level, and so on and so on. Okay, app CPU is a whole different level. My chosen non-maskable interrupts for pro CPU cannot be disabled. Highest priority. Well, probably we won't actually mask the system interrupts, because it might end up breaking the esp32, because watchdog timer is actually fires when we actually caught that thing in one of the series, probably, I can't really remember, probably here, when we made an endless loop and FreeRTOS fired the watchdog interrupt, because we wouldn't allow the FreeRTOS to do its work, because we were constantly blocking one of the cores, and it was like firing like, I want to do some work on this core, but it is blocked, and so on. So yeah, probably we won't want to really block or mask these timers. Well, it's interesting, but very exotic, you know. Yeah, and for app CPU as well. right side. These are the actual CPU interrupt lines. Pro CPU peripheral interrupt delivered to core 0. Core 0 to save context, jump to ISR, execute handler. So basically, this output, well, okay, we get the status. Okay, we get the status of the interrupt written in the status register, and we also get the interrupt itself. But what is the interrupt itself? What is it internally? Damn. The interrupt signal delivers to core 0, save context, jump to ISR, yep, and execute handler. App CPU peripheral interrupt, same thing, but delivered to core 1. Okay. Status registers. Which peripheral actually caused this interrupt? Okay, so now the full picture is understood. Interrupt matrix is used to bind the interrupt peripherals to CPU interrupts. This is done with the configuration register of each cores, which corresponds to app CPU and pro CPU. So there are two of them, core 0 and core 1, as you can call it. Then, when the interrupt happens, this matrix routes the interrupt peripheral to the CPU interrupt using those configuration registers, and it actually writes to the status register which peripheral actually caused that interrupt, and then we get the interrupt itself. Okay, so then the ISR is called, the context is switched, and so on and so on. Damn, that's actually an interesting topic. Yeah. What, 1 hour and 10 minutes almost. Wow. That's actually cool, guys. I'm not gonna lie, I actually enjoy to learn some theory stuff about that thing. But I guess I should actually end this video because it's already too that long, like 1 hour and 10 minutes. Anyways, I hope you enjoyed this video, guys, because I know theory is also important. Well, it's cool when we do some cool stuff like like remote LED control. It's also cool, and you can't really survive without practice, but you can't really survive without theory either. That's why I spent today's video just learning about interrupts, and I hope you guys learned something too, because like I feel like I learned a lot today about how interrupts are actually work. Not only even on that thing, not even on esp32, but also on, like, in general, what do they mean, and how they should be configured, how they usually configured. So that was pretty cool. So I hope you enjoyed that, guys. I hope you learned something. That's me. Hit the like if you learned something. If you, like, I don't know, subscribe to my channel to see more videos like that. Yeah, next video tomorrow. See you tomorrow, guys. Have a good day.